Hi students, so today is the start of the 11th lecture. We will study initially the branch instructions. There are two types of branch instruction. The first one is unconditional branch instruction and the second one is conditional branch instruction. So first we will study an unconditional branch instruction. As we know that typically in microprocessor the instructions are executed in a serial fashion. However, there are some instructions that change the flow of program. I will illustrate this with an example. Let's assume that there is microprocessor instructions like add, R3, R2, R1, subtract, R5, R6, R7, and then so this is a sequential instruction. So when microprocessor execute this instruction, the next instruction that has to be executed is this instruction. However, if we have an instructions like jump, or we give some label like label. So this instruction will change the flow of the program and it will jump to an address that is label. Let's assume that this label is defined here. So now if this is instruction 1, I1, this one is instruction 2, this one is instruction 3, and followed the instruction is I4, I5, and so forth, so on. And if this is an instruction I90, so if jump label, so the control will be transferred to instruction I90. So first I1 instruction will be executed, then I2 will be executed, and when jump label, so after that I4 will not be executed and the control will be transferred to this label, and the control will be transferred to this I90, and the next instruction that has to be executed is I90. So jump is an equivalent of go to statement in C or C++. So now this is an example of a jump instructions. If you look at this small fragment of program, it consists of some instruction 1, instruction 2, maybe this instruction 1 is add instruction, instruction 2 is a subtract instruction. So these instructions are stored in memory. Let's assume that the address of the first instruction, this instruction 1, is 1000, and we also assume that the size of each instruction is 4 bytes. So the address of the instruction 1 will be 1000. All these values are specified in hexadecimal notation. So the address of the second instruction 2 is 1004, because the size of this instruction is 4 bytes. So now this instruction consists of 4 bytes. And the address of the instruction 3 is 1008. So if you look at this fragment of the program, so the address of this instruction 4 is 100, C, and so forth, so on. So if you look at this, so if let's assume that the control of the program is here. If instruction 1 is executed, the next instruction that has to be executed is instruction 2, and then we encounter a jump instruction. When a jump instruction is encountered, the control will be transferred to label. Now what is label? Label is actually an address. So now this is a label and label is an address. So if you look at this fragment, so there will be some instruction, that is instruction I50, instruction 50, instruction 50, and this will have an address, and that address is label. So the control will be transferred here. If you look at this, what is start? Start is a label, and what is start? Start is a label, and it is an address. It is address of instruction 1, and the value of this start is, if you look at this, so start is an address of instruction 1 and the value will be $1000. Now if you look at this back is also a label. So now this is a label and this is an address of instruction 5. If you look at address of instruction 5, the address of instruction 5 is 1010. So this value will be $1010. So now if you look at an unconditional jump instruction, the jump can be forward or the backward. So now in this scenario, we are at this instruction and then the control will be transferred from this instruction. So in this case, the jump to a label, and this is a forward jump. However, if you look at this, when the control is transferred to here, to instruction 50, instruction 51 and instruction 2 will be executed. Let's assume that they are serially executed. Now we have a jump back. So now in this case, when this instruction will execute, the control is transferred back to this instruction. So this is an example of forward jump, and now this is an example of backward jump, and this jump is unconditional. It will not check any condition. Therefore this is an example of unconditional branch, and the example of unconditional branch is jump instruction. Now we will study conditional branch instruction. Before studying conditional branch instruction, we will study compare instructions. So what is the syntax of compare instruction? So compare Q and P. So compare instructions compares two different operands. This is operand 1, and P, this is operand 2. And based on the result of these operand and based on the values of these operands, it sets some flags. So it sets some flags. One flag is referred to as Z flag and another flag is referred to as N flag. So if there are three possible outcomes. The first outcome is that when Q is greater than P. The second possible outcome is that when Q is smaller than P. And the third possible outcome is that if Q is equal to P. So if Q is greater than P, so what does it mean? That Q is greater than P, it means that the result is positive. So when the result is positive, so now the result is positive, so the N flag will be 0. The result is positive, the N flag is 0. So if the result is positive, N flag will be 0. If result is negative, N flag will be 1. And for Z flag, if the result is equal to 0, Z flag is 1, it means the result is 0. And if the result is not 0, Z flag will be 0. So now if Q is greater than P, so the result is positive, N will be 0. And it is a non-zero, so the Z flag will be 0. So when Q is smaller than P, so it means that the result is negative. So when the result is negative, N flag will be 1 and Z flag will be 0 because it is not 0. When q is equal to 0, so z flag will be 1 because the result is 0. So q is equal to p. So when q is equal to p, z flag will be 1. So when we are comparing q and p, it will compute the result, and the result will be computed as q minus p. Okay, I will illustrate this with an example. So now there are three different scenarios. Let's assume that the values that are stored in register R0, R1, R2 and R3 are 65 in hexadecimal, 75 in hexadecimal, 65 is in hexadecimal, and the value of the content of R3 is 35 in hexadecimal. So if this instruction, so if we execute this instruction, it will compute result. So what is the result? Q minus P. So what is Q minus P? So in this case it will compute R0 minus R1. So when it computes R0 minus 1, what is the contents of R0? So the contents of R0 is 65 minus the contents of R1 $75. So if you look at the result is, so the result is negative. So when the result is negative, so for this particular example, the result is negative. In this particular example, the result is negative. The result is negative. So what will be the value of n flag? So n flag will be 1. N flag result is negative, the n flag is 1, and because the result is negative and the result is also non-zero, so when it's non-zero, so it's not 0, so z flag will be 0 here. So now we evaluate for this example for the second instruction. So it will compare R0 R2, so it will compute R0 minus R2. So what is the contents of R0? The contents of R0 is 65. And what is the content of R2? The content of R2 is 65. So what's the result? The result is 0. So when the result is 0, so in this particular example, the result is 0, so z flag will be set to 1, and because it is not negative, so the result is positive, so n flag will be 0. Now we evaluate this for another example. Now we are comparing R0 and R3. What is the content of R0? So we will compute R0 minus content of R3. So the contents of R0 is 65 minus the contents of R3 is 35. So the result in hexadecimal will be 30. So it means that the result is positive. Result is positive. So when the result is positive, n flag will be 0. And because the result is not 0, so z flag will also be 0. So these are three different examples when we are comparing two different operands q and p. So when q is smaller than p, so it's negative and flag will be set to 1. And in this example, n is equal to 0 and z is equal to 1. So based on these compare instruction, we can so now we will study conditional branch instructions, and in conditional branch instruction first we will study BEQ. So BEQ stands for branch if operands are equal. Otherwise, so it's a conditional branch instructions. So if you look at this example, so now let's assume that we are comparing R4 and R5. We are comparing, and let's assume this instruction is I1, and then it's followed by second instruction, branch equal process. What is process? Process is a label, and process, so process is a label, and it is an address. It is address of instruction I16. So process, so it will jump here, but it is based on the condition. So the jump will be made here if R4 is equal to R5. So it means that we can say that if R4 is equal to R5, so jump will be made to instruction I60. Otherwise, the condition is false. So in this case, in this particular case, the condition is true. So if the condition is true, jump will be made to instruction I60, else the next instruction will be executed. Next instruction will be executed, and what is the next instruction? So the next instruction is I3. So I will elaborate this with an example. So in this, so there are two scenarios. Scenario 1, in which the contents of R4 is 35 and the contents of R5 is 65. So they are both compared. So if you compare 35 with 65, what is in scenarios? They are not equal. So when they are not equal, so the condition will be false. So the sequence of instruction that will be executed, first the instruction I1 will be executed, I2 will be executed, and the condition is false. So it means that the jump will not be made, and the next instruction that is executed is instruction I3. So now in scenario 2, let's assume that the contents of R4 is 35 and the contents of R5 is 35. It means that both are equal. Now in this case, both are equal. So this comparison, so the condition is now true. So the condition is true, and the jump will be made to instruction I60. So the sequence of instruction that will be executed, first instruction I1 will be executed, then I2 will be executed, and the jump will be made to instruction I60. So there are various examples of conditional branch instructions. So now, if instead of equal, so if we say branch not equal, so it means that a jump will be made, if R4 is not equal to R5 from branch not equal. If R4 is not equal to R5. If we replace this branch not equal with BGT. So if we say, what is BGT? In BGT, a jump will be made if R4 is greater than R5. So if we say BLT, this is called branch not equal. It stands for branch greater than. So a jump will be made. In this particular example if R4 is greater than R5. Otherwise, if the condition is false, then this sequential instruction will be executed. So in BLT, so if we have another example like BLT. So if we replace this BGT by BLT, it means branch less than. So BLT. So in BLT, a jump will be made if R4 is smaller than R5. If you replace this BLT with BLE, so BLE, a jump will be made if R4 is greater or equal to less than or equal to. So it's less than or equal to. It's less than or equal to R5. So now this is a difference between conditional branch instruction and unconditional branch instructions. So in an unconditional branch instruction, a jump is always made, while in a conditional branch instruction, a check is made. So there are two types of branch instructions. So branch instructions consist of two types. One is jump instruction, in which an unconditional jump is made, while this is unconditional jump, unconditional branch instruction. An example of unconditional branch instruction is jump and conditional branch instruction. So the example of conditional branch instruction is branch equal, branch not equal, branch less than, branch greater than, branch less than or equal to. Okay, so now we proceed further. Okay, now we will study how we can interface a keypad with a microprocessor or microcontroller. So now let's assume a scenario that a microcontroller or microprocessor is interfaced with keypad or keyboard, and let's assume that the address map, this keyboard contains three registers. One register is called as SR. SR stands for the status register. CR stands for, so this stands for status register, CR stands for control register, and DR stands for data register. So now let's assume that we have a specification from the manufacturer that if SR is equal to 1, it means that the device is ready and some key has been pressed. Let's assume that we have a keypad or keyboard, and when we press a key, so in that particular case the SR will contain a 1. It means that some key has been pressed by the user. and then the value of the control register. So it can help us to configure the device as an input device or an output device. If the value of the control register is 1, so the device will be configured as an input. So in this example, we are configuring the device as an input. So keypad for keypad or keyboard, the control register value will be 1. And if CR is equal to 0, the device is configured as an output device. And what are example of output device? So if we want to configure to some other device, like for instance LCD, so in that particular example, the control register will be 0. And what does data DR stands for? DR will store the value of the key that has been pressed by the user. For instance, if the user presses some key like 5, so the data register will contain a value of 5. If the user presses 9, so the data register will store 9. So now this is our specification. So now what's our objective? Our objective is to write a program. What program? We will write an assembly language program that waits for the key to be pressed. It will wait for the key to be pressed by the user. So if it will, and it will store that value in register R2. So the keypad is interfaced with the microcontroller, and the address of the status register is 1000. The address of the control register is 1002, and the address of the data register is 1004. So what's our objective? When a key is pressed by the user, the value will be contained in the data register, but first we have to wait for the user so that he has to press a particular key. So when the user has not pressed the key, the SR will be 0, and we have to wait for some time until the user presses a key. So when the user presses a key, so the SR will contain 1, and in that particular case, please guess, so we have to continuously check or monitor the status register, and when the key has been pressed, the value is stored in the data register. So now we will write an assembly language program for this example, and so we know that when the control register CR is equal to 1, so the device is configured as an input, so we have to store a 1 in the control register. So how we can write a program? So now we can write a program. So now we will start with org $000. What does org stand for? It is the starting address of the program. So now this is some memory. So memory, and we are storing some instructions. So let's assume instruction I1, instruction I2. So the address of the first instruction will be $0000. So we'll start with org. So first what we have to do, so now we will also use some instructions. So if it means that okay, what do we say? Okay, so before starting with org, we will use eq directory, eq. So what? So if we say before explaining this, we will study eq. So what is an eq directory? Eq mnemonic in assembly. Let's assume that if we say that count eq 5. So let's assume that if we have some assembly language program and we say move R3 #5. This is an immediate addressing mode, and that's when move R5 #5 or compare R5 #5. It means that what we so if we have in this assembly language instruction, if we have count and count, so this count will be replaced with the value of 5. This count will be replaced with the value of 5. This count will be replaced with the value of 5. So instead of the equal mnemonic, if we use move R3 hash 5, let's assume if we have move R3 hash 5, move R3 hash 5 and move R3 hash 5, and if we want to change this value from 5 to 7, so we have to make 3 changes. Changes 1, we have 7 and 7. So if we replace this constant value with count and count, so we have to only make a single change. So we have to change this 5 with 7. So it means that all of the values will, all of the instances, all of this instance will be in this instance the count will be replaced with the value of 7, the count will be replaced with the value of 7, and the count will be replaced with the value of 7. So if we change the count to 11, all these values will be replaced, all this count value will be replaced with the value of 11. So if count is defined n times, so if count is defined n times in the code, so count is defined n times in the code, so we have to do only a single change instead of n changes. So we can save it for this example. So we can use some mnemonics, and then also to make the program more readable, so we can say that SR in this example, SR, this is SR, CR and DR. So in this example, SR equal $1,000 and CR equal $1,002 and DR equal $1,004. Okay, so now we also said it. Okay, if we also said that if we want to configure the device as an input device, so input equal, so if you want to configure the device as an input device, so the control register should be initialized with a value of 1. So input is 1. So input is initialized to a value of 1. Okay, so now, so we can start with the config. We can start with our program org$0000. So it means it is a starting address of our program. So we can start. So we can say move. Okay, so what we if we want to configure the device as an input device, so we have to move a value of 1 in the control register. So how we can initialize this memory location with a value of 1? So we will use absolute addressing mode. So we can say move CR, control register. So control register, what is the address of control register? So the address of control register is 1002. So this is the address of control register, and we want to initialize a value of 1, so we can say move CR. So this CR is our destination, and we want to initialize, so we will use immediate addressing mode. So we will initiate, so we can also write it like this, move CR1. So instead of using 1, we can make the program more readable, so we can replace it with like this, move CR hash input. So these two instructions are equivalent. However, this instruction is more readable compared to this instruction. Why we have used an input? Because we want to configure this device as an input device, and because keyboard is an input device. So what we can do, we can say like this, that we move CR hash input. So in this case, CR absolute addressing mode, we are writing to an address 1002, CR is equal to 1002 true, and we are writing a value of 1 because input is equal to 1. Okay, so now the device has been configured as an input, so we can also write some commands. So these are some command. Okay, configure. So we are configuring device as input. So we are also putting some commands to our code. So these statements will be ignored by the assembler. This only improves the readability of the program. R0 C status register. So we want to set it whether. So it means that if the key has been pressed by the user, so if this SR is 1, it means the key has been pressed, and if SR is equal to 0, so it means not pressed. So what we can say, we can also introduce another echo, like I say, key pressed equal 1. So it means that if the key has been pressed, so the value will be 1. If the key is not pressed, the value will be 0. So what we have to do, we have to move the contents of the status register. So status register, actually this is the address of the status register. So what we will do, we will move the contents of the status register into R0. So what we can say, compare R0 with 1, means that if it is equal to 1, it means that the key has been pressed. So we, instead of using 1, we can use key pressed in order to make our program more readable. Key pressed, and then we say, okay, if the key has been pressed, so we have to move forward, but if the key is not pressed, so we have to wait. So it means that if the key has not, if it is not equal, so it means that if R0 is not equal to key press, so cross not equal, wait. So the program will wait in the loop. So there are two scenarios. Scenario 1, when the contents of R0 is equal to 1. So if the contents of R0 is equal to 1, it means that the key has been pressed. And scenario 2, when R0 with a value of 0, it means the key is not pressed. So in this particular scenario, we have to wait. So we have to wait. So again, we will move the value. So we have to wait. So we have to wait here. We have to wait. So we have to wait if it's not equal to. So again, we will move the contents of the status register into R0. And we will compare the value with the value of 1. So if it's the key has been pressed, otherwise we have to wait for indefinite interval. So when R0 is equal to 0, so it means that the key has not been pressed. So if it's not equal, and So it has to wait in this loop indefinite for a very long interval of time. However, when R0 is equal to 1, it means that they are equal, so the condition will be false, and now we have to move the register. So when the key has been pressed, the value of the key pressed will be moved into the data registers. So now we can say, so in this particular example, so then we can move the value of R2 into data register. So when the key has been pressed, SR will be 1. SR will be 1. So we will come out of this loop, the control will be transferred here. So the control will be transferred here. In this particular example, the control will be transferred here, and the value of the value of the key press, let's assume that the user presses 5. So the value of the data register will be moved into register R2. So if you look at the memory map, so it starts with an instruction ORG, and let's assume that the size of each instruction is 4 bytes. So the size of each instruction is 4 bytes. So the first instruction, this instruction will be move instruction, move CR hash input. So this is instruction 1. This is instruction 1, move CR hash input. This has an address of $000. So the next address will be $0004. Let's assume the size of this instruction is 4 byte. So this instruction will be stored at a location move R0 SR. And what is this $004? Actually, it is the address of the wait instruction. And then $000008. So the next address will be compare R0. So the move R0 SR. So the next address, this instruction will be stored. Compare R0 hash key pressed, and $000C. So the next instruction was not equal, and $0010. The next instruction move R2 DR will be safe. Okay, so in this case the contents of this will be moved into this register. Okay, so now we will write an assembly language equivalent of this C++ program, in which we have some variable test. This variable test is actually the contents of the data register, and there we are scanning some value from the keypad and storing that value in variable test. So and that value is stored in the data register. Now we have a switch statement, and now the switch statement is actually checking the value of the test, and based on the condition. So if test is equal to 65, if the value of the test is equal to 65, so the instruction that has to be executed I1, I2, and I3, and then the control will be transferred to this statement I10, I11, and I12. If the value is equal to 95, so now in this case, so if there are three possibilities, so if the value of test is equal to 65, so the instruction that will be executed are I1, I2, I3. So this condition is true, then the control will be transferred here. It will come out of the switch statement, and then the instruction will execution I10, I11, and I12. Now, another case, if test is equal to 95, so the instruction that will be executed is I4, I5, I6, I10, I11, and I12, and else and else, in the case of the default statement, so the instruction that will be executed are I7, I8, I9, I10, I11, and I12. So now we have to write an assembly language program for this program. So what we have to do, now we know that we want to interface a keypad, and we have 3 registers within the keypad. The first register is refers to the status register, the control register, and the data registers. SR is initialized with a value of 1000. Control register is initialized with a value of 1002, and data register is initialized with a value of 1004. And actually these are the addresses. So 1000 is the address of the status register, 1002 is the address of the control register, and 1004 is the address of the data register. So we have already used a signal that is ready. So if the status register will contain a value of 1, the device will be ready, and if the status register is 0, the device will be 0, the device will be not, or the input keypad will not be ready. And if you want to configure the device as an input, so we have to initialize a value of 1 to the control register. So we are configuring. So what we have to do, so we want to configure the device as an input device. What we have to do, so we have to move CR with the value of inputs. We are using an immediate addressing mode. So in input is with 1. So the CR will be initialized with a value of 1. So it means that the device is now configured as an input device. Now what we have to do, we have to check the status of the device. So now we are in this statement scanner, we have to check the status register. So what we have to do, now we can say move, and we can use some temporary register R0. So we move R0 into SR. So what we have to do, we are transferring the contents of this register, into R0. So now we are compare R0 with ready. So if the device is ready, so if the device is not ready, so it will move. So we have to wait. So we have to wait for the key pressed by the user. So branch not equal, it will jump on the page. Branch not equal, wait. If the device is ready, so this status register will contain a 1. So this will contain a 1. So it will come out of the loop. So now we can move into some register R1, move R1 and data register. Actually, when this status register is 1, it means that some key has been pressed by the user, and the user presses some key. Let's assume that the user presses 65. It may press any value, so it may press 65. So it means that this value 65 will be moved into register R1. If the user presses 91, so register R1 will contain 91. If the user presses 76, so the value of the register R1 will be 76. So what we have to do, we are moving the contents of the data registers. Actually this R1 will contain the variable test. Now we have to compare this R1. So we have to compare this R1. So we have to compare R1 with the value of 65, with a value of 65. So if it is equal, so branch equal. So if it is equal to, so we will jump on code 1. What is code 1? So code 1 is actually a label, so we can define some new label. So this config is a label, wait is a label, so we can define some code 1. So code 1 is here, code 1 is here. So if you look at the code 1, so which instruction will be executed? I1 will be executed, I1 will be executed, then I2, then code 1, then I3, and then after that we have to jump to this I10. So we can also have jump exact code. So we can also write here some this jump exact code. So we can also have this exact one minute, I have to, we can write it here. So code 1, so I can write I1, then I2, then I3, and then jump exact code. So we can have another level of exact code. So this is exact code. So if you look at this is exact code. This is code 1. This one is code 2, and this one is code 3. So what will be the instruction that are executed on the exact code? So this is I10, I10, then I11, then I12. Okay, so if this R1 is equal to 65, so the control will be transferred here, and then I1, I2. If it's not equal to, now we have compared R1 with 65, now we have to compare with 95, so now we can compare R1 with 95, so if it is equal, we have to jump on code 2, so now this one is the code for code 2. So in code 2, if you look at code 2, if it's not equal, so we jump on code 2. So which instruction will be executed in code 2? I4, I5, and I6. And then we can say jump exact code. Okay, so now we have to write it a little bit. Code 1, I1, I2, I3, and jump exact code. Now we have to compare. Okay, so if the condition is true, this condition is true, it will jump on the exact code and then jump exact code I10, I11, and I2 will be executed. Now we have to compare R1 with 95. If this condition is false, so then R1 will be compared in 95 and the control will be transferred to code 2. So the instruction level will be executed I4, I5, and I6. And if this condition is not true, so now we will jump on the default code. So now this is our default code. So what will be executed on default code? So on the default code, the instruction level will be executed I7, I8, and I9, and jump exact code. So now if you look at this code, this first, the keyboard is configured as an input device. Now we have moved the contents of the status register into R0, and here we are continuously checking the value of the status register. If the device is ready, so the control will be transferred here. If the device is not ready, so the keyboard will be in unlooping fashion. After that, when the device is ready, the value will be stored into the value of the variable will be stored into the data register. So now we have moved the contents of the data register into register R1. So now in this case, this switch is, so R1 will contain the test value. Now we are comparing R1 with the value of 65. We are comparing R1 with the value of 65. If it's equal, so it will jump on code 1. So the instruction header will be executed with I1, I2 and I3, and then it will jump on the exact code. If it is not equal to 65, so then it will compare with 95. So if it will compare with 95, it will compare with 95, then it will jump on code 2, the instruction header will be executed with I4, I5 and I6. And in the default case, with both conditions are false, this condition is false and this condition is false, so the control will be transferred to the default code and this line. And when this default code executes, so the control is again transferred on the exact code. So you can test it with different conditions or different scenarios. Okay. So now we will write an assembly language program that will sum 100 elements in the array. Typically the elements of an array are stored in memory. So now this is an array and it consists of 100 elements. So this is the first element E0, the second element E1, the third element E2 and the last element E99. So this one is the 100 element, 100 element, and we want to write an assembly language program that sums all the elements of the array and store them in some register R2. So at the end of R2, so R2 should be equivalent to E0 plus E1 plus E2 plus so on plus E99. So at the final, the sum of the 100 elements of the array is R2. So we have to store this sum into register R2. So how we can write an assembly language program? So first we can use some directly count. So we define an equal to count equal 100. So count is mnemonic, or is a constant that has a value of 100 because we want to have a sum of 100 elements of the array. And now we will have a base address. So base address equal $1000. So base is actually the address of the first element of the array. So what is base? Base is the address of the first element of array. So now this is equal to base. Base is the address of the first element of the array. This is the address of the second element of the array. This is the address of the third element of the array, and this is the address of the fourth element of the array. So now we will write a program. So now let's assume. So if we want to find the elements of the array, so we have to initialize some variable. Like let's assume that we would like to have some variable. So this variable will be equal to sum, and we store this variable into register R2. And we will also like to have a temporary variable. So this temporary variable is equal to like R1 that will contain the. So now we have different iterations. So we can have. So in this case, some address register will be pointing out to this A0, will point into this base address. So now we have this A0 is the address of the first element of the array, and then we can have some count. We can store this count into register R0, and then we can store some in some register R1, or we can also use some another register R2 and 10. So okay, so if we write a C++ program for this program, so we have to store So we can have different iteration of the program. Let's assume that I is equal to 0. So I0, so A0 will point to the first address, $1000. So what should be the value of count? Count is equal to 100. What should be the value of sum? Sum will be 0. R2 should contain the elements of the first element, R5. So when the iteration is 1, A0 will point to the next element, that is $1004. What will be count? Count should be decremented 99. What should be the sum? Sum plus temp, that is 5. Now temp will contain the next value, that is 6. Similarly, I is equal to 2. The address should be now 1008. The count should be now 98. The value of sum 5 plus 6 is equal to 11. And then temp will contain the elements of the third element, that is so forth. And in the last iterations, when I is equal to 99, so the count will be 0, and the sum will contain the sum of all elements of the array. So how we can do it like this? So we can start a program, org $00000. So now we can move this value A, move A0, hash. So at the first iteration, A0 will contain the address of the first element of the array, and base is equal to 1000. So A0 will contain, so this is A0 will contain 1000. So now we can initialize this R0 with count. So for the first iteration, the count will contain a value of 100. Okay, so now what we have to do, we have to move the elements of the first element of the array into some register R2. So now we will move R2, it's the first element, A0. So which addressing mode we will use? We will use register indirect with post increment. So in register indirect with post increment, the memory address which is pointed out by A2. So now what we do? So A2 now A0 point to this memory address. This value will be accessed. What is the value of 5? 5 will be moved into R2, and A0 will point to the next element, so it will point to the next element. So we are using register indirect with post increment address. Okay, so now at first instant, A2 is pointing to this memory address. The value of the first element is moved to the register R2. So in this point, at point R2 will contain the first element. So now what we have to do, we have to we are using a register sum. So before this instruction, move R1 the sum is initialized with the value of 0. So the sum will be 0. Move R2 is a temp, R2 in R2. So the address register will point to this memory location. A2 contains a value of 100. It will point to this memory location. 5 will be moved into R2 for the first iteration. Now what we have to do, we have to decrement the counter, that is R0. So initially the R0, at this point R0 contains 100. For the first iteration, now R0 will be decremented, and the new value will now be 99. And in the next iteration, the new value will be 98, and then 97, and so forth, so on. And then we have to add the sum R1 and R2. Now we have to compare R0 with 0, and if it is not equal, so we have to move to process. If we have to move to this process is a label, so the jump will be made here. So in the second iteration, the count will be, that is R0. In the first iteration, the value of R0, that is the count, will be 100. In the second iteration, it will be 99. In the third iteration, it will be 98, and so forth, so on. So when it reaches 0, so it will come out of the loop, and then we can at the end of this loop, all the elements of the array has been summed. So now we can display R1. R1 contains the sum of R. So in the first iteration, R1 will contain 5. The second iteration, R1 will contain 5 plus 6, 11. In the third iteration, R1 will contain 11 plus 2, 13. And in the fourth iteration, R1 will contain 16. And in the fifth iteration, R1 will contain 16 plus 9, 25, and so forth, so on. So in the end of this all iterations, the register R1 will contain the sum of all elements of the array, and that's the advantage of using the equal symbol. Like, let's assume that if we want to find the elements of 200, that the sum of the 200 elements of the array, we have to just make a change here, and then we can initialize it with 200. And similarly, if we change the base address of the array, let's assume that this base address starts from 200, 2004, 2008, 2002. So what we have to do, we have to change the base address in this particular example. So now this base address should now be initialized with 2000.